Another topic is called the Harrow-Hasidim-Lloyd algorithm or HHL algorithm. This two part. Actually, these two algorithm itself can take to understand properly should take ideally 2 months. Okay, there are lots of protocol insights, but as we in the previous class. Um, as we have seen how the QFT is implemented and what's the philosophy behind the QFT algorithm, right? And its importance in source algorithm, like factoring algorithm, source algorithm. So as I promised to yesterday that I'll be showing some Qiskit demo. So and typically, if you look at the QFT construction yesterday, so today I'll be. So while we study the QFT, quantum Fourier transform, and yesterday we have seen an equation. That equation is important. I'm just writing the final expression. And similarly, today also we'll derive the quantum phase estimation algorithm step by step, right? As part of this class. And HHL algorithm has a lots of protocol, but I thought to save some time and all, I'll give a presentation, short presentation in 10-15 minutes, and I'll share the actual paper on HHL that is published in 2009 on the solving linear system of equation using the quantum protocol called HHL. Okay, so that part, the detailed paper I'll be sharing so that you can have a look into the paper. So please keep this link with you in the chat box. I am pasting the journal paper link, as well as some sort of very small 2x2 system implementation in Qiskit, because these are fault tolerant algorithm. So you cannot quickly implement this algorithm for large system. We need bigger and fault tolerant quantum machine for that. So normally VQE variational algorithms, QAOA optimizations algorithm, SQD algorithm. So there are some algorithms known as the near-term quantum algorithms. So I'm not taking those algorithms in this course. Most likely with other speakers, Dr. Ritojit is covering some of those interesting topic, and please listen to his lecture, and he's a very leading expert in our team. So he can demonstrate the implementation of all those algorithms in Qiskit. So the topics I am taking, these are the fault tolerant quantum algorithm. You will likely to see this implementation for large scale in upcoming years. Okay. So 3 links I pasted in the chat box. You can please copy these links, right? Both the Qiskit tutorial as well as the like some smaller system applications is given. And today I'll show how to implement the QFT algorithm in Qiskit. Okay. Before that, I'm just writing the final expression, right? Because the circuit design itself considers two critical steps, right? So what was our final expression yesterday? That we had something like this: x tilde Kate equals to no, you need to collect this paper from someone, like from some IITs or somewhere. I cannot share the paper. That is, I mean, beyond the policy of the journal publishers. Please take it from your institute or somewhere, right? I cannot share the PDF. Sorry for this. So I just shared the link. Somehow you need to download, right? So that is difficult for me. Yeah. So 1 upon square root n Ket 0 plus the first qubit, we need to encode 2 pi ix by 2 Ket 1, right? And tensor product with the, I'm writing just one below another, okay, such that it is easier to understand. Tensor product with 0 plus e power 2 pi ix by 2 square, get 1. Qiskit is accessible to everyone. Just you need to download the any Python environment and just to do this pip install Qiskit. I think this is already demonstrated in all the courses QT 1, 2, 3, 4. All the courses this is shown, like how to install Qiskit, the basics tutorial. So this is free. Using Qiskit, circuit design, simulation, all are free. You don't need to pay anything. This is an open source software from IBM. Okay, but the hardware, if you use the hardware, so there may be some price, but for this tutorial, hardware is not necessary. And so on. And the final expression was 0 plus e to the power 2 pi I x by 2 to the power n get 1, right? So this equation, because so if simply x takes the value 0 or 1 accordingly, someone is saying video is not coming. Can anyone confirm my this display and my voice is clear?
Yes, sir.
Yeah. So those who are not like getting the video, please rejoin. Maybe technical problem. Thank you. So we have seen this expression, and we try to understand that what sort of quantum circuit operations we need to do. So left hand side, this is the mathematical expression, right? And right hand side, if we look at the circuit part, two kinds of circuit yesterday we have discussed. One is the Hadamard gate itself, right? So, and in circuit, it is represented as H, okay? And this is a matrix, and the values are 1, 1, 1, minus 1, right? And normalized by 1 by square root 2, okay? And another gate that is the controlled rotation gate, basically. Controlled rotation gate. This one is important because when the qubit is 0, it does nothing to the phase, but when the qubit is 1, it adds a particular phase. And normal phase gate, only U rotation gate we have seen. U rotation with power k is written as 1, 0, 0, e to the power 2 pi I by 2 to the power k. Okay. So this is the second part, right? And if I say the controlled gates in circuit. So for example, if it is a single C0 gate, right? The C0 gate definition is given as 1, 4, 0, 0, 1, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. And if I look at this particular matrix, first half of the matrix looks like an identity matrix, right? So just first half of the matrix looks like an identity matrix, and the second half of the matrix, this part is a X gate, right? Pauli X gate. And this part is an identity matrix. So this is also defined as the outer product of the vector 0, 0, tensor product with I, plus outer product of 1, 1, tensor product with X, Pauli X thing, where X is your this 0, 1, 1, 0, and identity matrix is 1, 0, 0, 1. Okay. So the philosophy is, if you have this particular qubit, first qubit is 0. If the first qubit is 0, does nothing to second qubit, okay? Second qubit state, or second qubit, it does nothing to second qubit. And if first qubit is 1, then it flips the second qubit, right? So that means if I have a state, say 0 0 plus 1 0, if this is my quantum state, right, and I apply a C naught gate here, then what will be the output? So the first quantum state will be intact because the first qubit is 0, and the second quantum state, that is 1 0, because the first qubit is 1 in the second quantum state. So this 0 will flip to 1. So the second state will be 1 1. So in circuit it looks like this. So you have a Hadamard gate here. You start with a 0, right? And another state says 0. So what is the state here? 0 0 outer product, I mean the tensor product, right? And here this qubit 0 becomes your plus state, right? And this 0 does nothing, right? So finally this particular state will be plus and 0 state. So which is equals to 0 plus 1 by square root 2, plus state is 0 plus 1 by square root 2 tensor product with this 0 state, right? By square root 2. So this is basically 0 0 state plus your 1 0 state, right? And normalized by 1 by square root 2. Now if you apply a C naught gate like this, so this C naught gate is controlled with the first gate, right? First particular qubit, because this is the first register, and this is the second register line. Okay. So you apply the X gate as a control to the first qubit known as CX gate, controlled X gate, right? And when you apply this particular 4x4 matrix that I just shown here, this one, right? So what will happen when you apply this CX gate here, then particularly this 0 0 will be 0 0, and this 1 0 will be 1 1. Second qubit will flip if the first qubit is 1, right? This particular state is known as the Bell state, right? Bell state. So similarly, there is something called phase trick. I'll just I'll explain what is phase trick just in the quantum phase estimation. But the philosophy is, so you can have suppose you start with 0, start with some 0, you can apply Hadamard here. So you will get a plus state here, right? And instead of this CX gate, now I will apply CU gate. This is known as controlled unitary gate. And so earlier I suppose this is theta, right? So this state at this particular point, my state was 0 0 plus 1 0, right? And what will happen? Suppose I initialize this particular quantum register with the state psi, right? So then what is my state here? My state will be plus psi state here, right? It is 0 psi plus 1 psi upon square root 2 at this particular step, right? Once I apply the CU theta gate, controlled unitary gate, what will happen? The first quantum register will be intact, plus because in the second quantum register 1 psi, this 1 will be 1 into r theta into psi. This will be our final state. So this r theta is your this, if it is k, for example, if it is k, then it is 1 0 0 e to the power I 2 pi. So this was the definition, 2 pi I by 2 to the power k by 2 to the power k is the gate representation. So the Qiskit part will be very simple, because in the Qiskit code, when you'll be writing the code, so just you need to do that. You have 2 qubits. So you have to take that. You have a quantum circuit QC equals to, I will write the code, quantum circuit, and you will be taking 2 register, right? In the first registers, you have a Hadamard, QC dot Hadamard in the first register. Initialize the first position at 0. And between and the second registers, you have done nothing, right? So then between first and second register, you have applied a CX gate, CX between 0 and 1, right? And then you are doing the quantum measurement, right? Wherever you do quantum measurement, accordingly, you just need to write QC measure either all or what, like particular qubit you have to mention. So this will be your pseudocode for this circuit, similarly for this particular circuit. So what effectively we are doing, two kind of operations. One is along the qubit, if I increase the number of qubit, right? So I am applying Hadamard first of all for the quantum Fourier transform. Secondly, I have to apply controlled unitary gates, CU gates, right? So that is this particular equation is telling, because I have to add this particular phase 1 by 2, 1 by 2 square, 1 by 2 to the power n, right? As well as I need to create the superposition state. So let us do a Python code. If you have a your some this environment with you, like either you can write in Anaconda Jupyter notebook. If you have a Jupyter notebook, for example. So Jupyter is fine. Spider, if you have any of the environment, Spider or anything, I will write in VS Code. Okay, if you have VS Code, or in fact, those who haven't downloaded, you can directly open your Google Colab and just download these certain packages. So you will write the code. Wherever you will get the error, just to do pip install that package name. Okay, you will get that particular package to run your code. And to open the Google Colab in your browser, you need to have your Gmail account open. Okay. So I'm stopping this theory part here. I'll come back again for the QP and the other presentation part for today, like the HHL algorithm. So let's go back to this coding part. Okay, you audience need to, because yesterday I got a request to show the code demonstration. So for that, you need to have the laptop with you. I'm just keeping the chat box with me now in my another window so that I can interact with you. There are 365 participants. Okay, great. How to open this interface? Exactly, that was I was just telling. Either you can open Google Colab or your any Jupyter notebook, whatever it is, right? So, okay, those who don't have the thing with you, see. So let me share you an instruction sheet as well. Okay. Think I thought that this is already installed on laptop, because in all previous QTs this was already there, right? But not a problem. I can share you the instruction sheets as well. Recently, I presented in a workshop. This chat box, probably I won't be able to share that let me share with Professor Pillai sir if he can share the instruction sheet. Okay. So let's start. So we need to install those who haven't installed the thing. So you can install pip install Qiskit and these are certain packages. Okay. Then Qiskit here because we need to run on the simulator. Can you see my laptop screen or shall I increase the size? This is fine, right? Pip install Qiskit here, then Qiskit service runtime. Service runtime and okay, yeah, but better to install directly the IBM runtime. So these are some of the packages we'll see like and Qiskit visualizations probably. So some of the packages we need to install, but those I think those who have already installed, they won't have any problem. Otherwise, you can install these packages. So we need to call certain things called quantum circuit from Qiskit here, import here, runtime, sampler, estimator. Qiskit here we have to implement the state vector simulator and Qiskit visualizations, Qiskit import to state vector. So these are certain packages you can copy paste. So I'm just giving in the chat box and no, always copy paste thing I cannot do, but some of the time saving thing I will do. Okay. Because I don't have every time copy pasting thing to give. I will write the code directly. Okay. But don't worry, I'll be sharing the code after this class. That is not an issue. So those who are new, for example, to design a circuit or something like that, you just need to do just name a variable as quantum circuit QC as a quantum circuit, name it as a variable. And then you can do like quantum circuit, say with two registers and just let us just print a simple just Bell state circuit for now, right? So before going to QFT, so QC dot Hadamard just we have seen right in the first qubit, and then QC dot CX control X get between first and second qubit, and just let us see the picture how it looks like. MPL. Just check that you can print this simple circuit, a Hadamard and a C naught. It's a very simple one, just to test that your code is running. Okay. Just I have taken two registers, QC equals to quantum circuit 2. Then first, in the first line, I applied a Hadamard gate H. And between first and second, I applied a controlled NOT gate CX. That's all, right? And we are printing it. If yes, then let us try to design the QFT. Okay. So of course, there is direct functions to QFT, but we can try to write our own function. Say my QFT, for example. And what we need to give, we need to encode the number of qubit, right? You can write the function like this. So what are the things we have to design a quantum circuit QC dot or QC equals to quantum circuit. And now this can be any number of qubit. Yeah, you can do in IBM, but IBM is kit composer. If it is a coding environment, you can continue that. So I'm not sure what you are talking about. But better you if you write the code with me, you will understand how the code is written. Otherwise, just copy pasting will not help to learn, right? Because only there will be 6, 7 lines of code, and I'll explain each and every line. So first we are creating a circuit. Like in here, I have created a circuit with only 2 qubits. Now we are creating a circuit with any number of quantum register num qubits. Okay. You may do, but scaling might be problem. So then um, we have to do two kind of operation. One is the Hadamard gate, and then control unitary or controlled phase rotations, right? So let us do that for say qubit in range of num qubit. I'm going slow so that you can follow me. QC.h. So I'm taking a variable qubit, and that qubit can take any number or in the range of num qubits. So it will take 1, 2, 3, 4, 5, 6. If you take 6 qubit, for example, and each qubit, it will apply the Hadamard first. Then for other qubit in range qubit plus 1 to num qubit plus 1 to num qubit, qc.cp, controlled phase gate applications, right? And with the phase angle np dot pi by 2 to pi by 2 into other qubits minus qubit, comma other qubit, comma qubit. So np dot pi by 2 other qubit minus qubit. So I have to sequentially input the control phase gate from first qubit to onwards qubit. So every time, so e to the power say theta 1 into e to the power theta 2 will be effectively e to the power theta 1 plus theta 2, right? Like that way, if you look at. So if first you apply a Hadamard, and then there is a other set of qubits where this phase gate will be sequentially added, right? Then I have to do num qubit. Yeah, np dot pi is constant, right? Pi np num np I have just defined as numpy, and pi is the 3.14, right? Num qubit by 2. So this is an additional step we do. I haven't told this thing because in Qiskit, the configuration is that we start from bottom to top, this approach. So the information, the bit string that finally you get is a reverse of the original one. So for that reason, we need to swap the informations between the qubits. So basically, the first information will go to the last one, and last information will go to the first information. So this is a swap operations of, this is just for the ordering purpose. Okay. So this is our QFT circuit, and now we'll see whether this works or not. Okay. NP.pi is a predefined constant, so you can take NP.pi. Simply pi also you may take, that is not an issue. So I'm using NumPy because sometimes in Python there are certain packages mismatch and all. So safer to take NumPy. But I mean, you can take other things also. You can check it. So now let's test this code, whether this circuit actually works or not. Let's take num qubit equals to say 3 qubit, right? And suppose our initial state that computational basis. So if it is 3 qubits, so how many quantum state it can create? So it's equivalent to 2 power 3, that is equals to 8 basis states, right? So I can create 8 basis states. So classical state I should consider say 0, 1, 0 if my state, right? So I can write this state as suppose 0, 1, 0, so I have to write all the values here. So a corresponding state vector for this 0, 1, 0, maybe you can write this way, right? So where state 0, 1, 0 is 0, 1, 0, 0, 0, 0, 0, 0. So suppose this is my state and I want to apply the quantum Fourier transform that we just designed here, okay, to this particular state, and we want to visualize what is happening, right? And we just wrote our one function. So with the user defined one, right? User defined QFT, we'll apply this. So now our circuit is my QFT was our function. Our function name was this one. And we have to apply this to num qubit, right? Now, initial state equals to state vector of the state. I'm just encoding using the state vector functions 0, 1, 0. Those who are taking this, for example, some 8 values of a sinusoidal signal, you can use either state vector, or there is another command. So I'm just writing that comment here. You can do circuit.initialize. This function also valid where this is your circuit part. Here it is, for example, this is my circuit, then this can be circuit.initialize. But here I have taken directly binary string 0, 1, list all are 0. So either is fine to use, right? Then I can write circuit equals to, I already have an initial state, right? And initial state can evolve, right? And the previous circuit. So in the beginning day, yesterday, I told that there are in a circuit basically two things. You have to encode the information, and then there is a evolution, right? So you are evolving this circuit, and that particular circuit you are applying the initial state vector to evolve accordingly this particular circuit. This means this is a unitary matrix times the initial state vector, right? And that you are storing again in the same variable circuit. Okay. Or you can name it say circuit 1, for example, for simplicity. And then Is it converting the classical information? Yes, you are storing it into the qubit informations, right? After applying the transformation. So we have taken 3 qubits, num qubit equals to 3. We have applied this, right? So just give me a couple of seconds. So you can write this way, or this is also fine. So my qubits num qubit, sorry, 101. Yeah. So what I have done, same thing. I mean, this is fine. The same thing I just, because of the confusion of the variable name, I just put the QFT circuit instead of circuit. That's okay. And just I put another variable name, that QFT state, for example. So initial state was defined like this. Initial state is a state vector encoding of the binary bit string 0, 1, 0, all this thing. And then I applied my QFT on num qubit, right? Directly on the num qubit. So this is the direct QFT circuit, that we have designed. But the encoded state was this initial state, right? Now let us see the bigger picture. So here, if you see in the circuit, so see here, it's a bottom line. So the qubit 0, qubit 1, and qubit 2. So the first I have taken a particular Hadamard, then I am doing the pi by 2 rotation, so that if you can see like 2 pi I by 2. And then there is a pi by 4 rotation, CU, basically control unity operator with phase pi by 4. In the second Hadamard part, so if you look from bottom towards the top, you see just in the last qubit you have only a Hadamard transformation. It's like if you look at the equation, this is your first term, right? Only you have an Hadamard matrix. So just you take the mirror image. Suppose there is a mirror in the bottom, and this circuit is flipped along the horizontal axis. Then you can see in the first basically part here in this Q2 register should be your beginning, and this you have applied only Hadamard is giving you the solution. Next part you have an Hadamard, of course, and there is a there is a second part. There is an Hadamard, and additionally, so you have one rotation angle pi by 2. In the first qubit, that means basically the third equation term, as you have a Hadamard, you have a 2 control rotation grid, right? So your information is basically in the reverse order. And to make it in the forward order, what you have to do is basically a swap operations. That means this last set of operations will come first, and first will come to last. Middle will be in the middle, right? So that's why this block of the equations are inserted in this particular QFT implementations, right? So this is just our like direct implementation of what we are thinking, right? Similarly, there is a direct, you can call the QFT functions from Qiskit using this command, this qiskit.circuit.library import QFT, right? And and you can directly call these functions and do the same thing without any problem. So Qiskit QFT circuit, you apply the QFT on the num qubits. So and you do swap operations, approximation, decompose, and then you evolve with Qiskit circuit functions. Okay? So let's print this. So the same circuit you can look at here. So this is what we manually designed. And this is what Qiskit is giving us, right? Just a different way, just Qiskit inbuilt function, right? Same thing. The solution is the same thing, just design wise it looks a bit different. Now let's do a real applications of this quantum Fourier transform. Suppose like identify the frequency component of frequency component of sinusoidal signal. Suppose signal using quantum Fourier transform. Let's do this experiment. So suppose let's take 8 points. Okay, 8 points let us take because this is fine with 3 qubits, but you can take say to any number of points in power of 2, 16, 32, or any higher number. So here let us take for simplicity 3 qubit case. So eight data points you can encode simply. So first, what I have done, I have defined a sinusoidal signal sine to in pi x by number of points for x in the range number of points, right? In this way. And then the important step is first step to encode the information, what I have to do, because the values that this signal is taking, for example, if I print the value, print signal, if I do, so you can see this float numbers, and their sum may not be equals to 1, right? For example, if I also do print sum of the np dot sum of say signal, okay, it is in fact 0 because I'm taking a full periodic signal, right? And the total amplitude sum equals to 0, right? So that's more problematic, right? So what we have to do first, what we'll do, we'll find the norm of this signal, right? And then we'll normalize this particular signal, right? So then we'll encode the signal into quantum circuit like this. So QC signal is quantum circuit. This way we can design, suppose this is the name of our quantum circuit, QC signal. I mean circuit, quantum circuit for the signal. And how many qubits we need? We need, there are 8 points. So you can directly take, say, quantum circuit 3, for example. You could take this equals to quantum circuit 3. That is fine enough. But in cases, suppose this value, right? Sometimes this might not be in power of 2, right? Then we have to convert this. So what I have done, log 2 base length of the signal. So I just have done log conversion, then nearest integer of that, right? So this is another way, or you can take the ceiling function of these things also, right? So those who are facing difficulty with this, you can directly write the second line of the code, okay? And then what I have done, I have initialized the circuit qc.initialize, encoding the signal in the quantum circuit. How I am encoding? So I have computed the norm of the signal, and I have divided that norm with that particular signal vector. So signal is defined in this way, right? And what I have done the normalization of that signal. So normalized signal that I have written signal norm, right? So now if you see the sum of this, for example, sum of the np dot, it should come 1, not sure. Let's check, theoretically it should be 1. So np dot float 6400, but it's again coming 0. Okay, so because it's sinusoidal even after the normalization, this sum is coming at 0. That's because of the nature of the signal. That is not a problem. But in general, what I have done here is basically I have normalized the signal component, so I can directly print here, print this values here. So these are the component of the signals, right? So 0, 0, 0, 1. So because the sinusoidal looks like this, so the sum is coming as 1, 0. That's the other thing, because I haven't taken them as a normalized square. So if I would take the square of this, that won't be equals to 0 sum. So that's another constraint for this particular signal. That's okay. That is not an issue. So now I designed a quantum circuit and I initialized these components, right? I have 3 qubits, 0, 0, 0, 0, 0, 1, 0, 1, 0 to up to 1, 1, 1, right? And these are the probability amplitudes that I need to store in the qubits. For that, the command is QC signal initialize. This is your normalized signal, and I am encoding it into the circuit QC signal dot qubits, so individually, right? So then I will up. So till that, what is the circuit? The circuit looks like this. So to see the circuit, I have to write MPL. So it looks like this. So earlier you have a signal like this. You have encoded in the quantum state vector get psi. So now you can see you have 3 qubits, but you have encoded 8 amplitude levels, right? So this is called the amplitude encoding. This is a very efficient encoding in qubit. It can encode exponential data in n qubit, 2 to the power n data in n qubit, but it requires a huge number of quantum gates to do that. If you decompose this circuit, if you ask how it is doing, so you see there are lots of operations they are basically doing. So even I can decompose more probably. So there are so many multiplexers, many other things are here, right, in this encoded technique. So we are not going in deep of that implementation, but just we are looking that we have a state, quantum state, and it has an encoding versions, and the encoding state state looks like this, right? So now once you have that, now let's apply the quantum Fourier transform of this particular state vector. So we'll apply the QFT of the QC signal and the qubits. And then whatever we get, right? So we get the final state vector as the state vector we use to simulate it, right? To simulate the signal on the simulator. We need to simulate the circuit on the simulator, and then we can show the plot. So once you simulate it on the simulator, so what we have done, I have an encoded signal, right? I have encoded the state like this. Then I apply the quantum Fourier transform on particular this state. Once I have done that, I stored in a variable, you can say. Basically, this basically a QFT circuit, ISS circuit or QFT circuit, we say. And you can decompose, you can basically once you get this particular circuit, then you can compose this QC signal dot compose in this way also. This is just an additional line. You may not do that. That's okay. But this QC, after composing, we need to run on the simulator. And after running in the simulator, you can just check how the frequency components are coming, like the frequency indexing I have done. Okay. So QFT magnitude, the absolute value in QFT state dot data in state of binary string, and I have done a bar plot. So frequency index, this is, you can think of a frequency index. So like a sinusoidal signal, right? So if this is the 8 points you have, and if this is your middle point 4, right? So left hand side, there is a frequency component, and right hand side you can see another frequency component, right? At plus FC and plus minus FC, right? So these are the two components you can see after quantum Fourier transform here, right? So to estimate the frequency, what we do, we find the dominant frequency. So in this particular case, there is no noise, nothing. This is an ideal case. You can pick any one of them. So typically we say, what is the arc max of these magnitudes, as we call it as the dominant frequency term. And we just see that, okay, the dominant frequency is 1. So it's basically 1 by, we calculate the frequency as your dominant component, dominant peak, by 2 to the power n is the formula. Okay, 2 to the power n. Now 2 to the power n is also to number of points. That is here 8, right? So dominant frequency index divided by 8 is coming as 0.125 as your estimated frequency for the sinusoidal signal, right? So this is an applications of the QFT. I'll share the notebook. Don't worry if you have missed some part of the code. That is not an issue, and this is just an demonstration of the QFT circuit, right? So again, QFT is a fault tolerant algorithm. So for large scale application, if you are thinking to use quantum Fourier transform for some of your research problem, so up to 12 qubit, 13 qubit, you can easily go and show certain interesting result. For more number of qubits, for example, if you are using say 12 qubits, right? So that means 2 to the power 12 is the number of C naught currently is required. I mean, roughly, right? So which is equals to 4,000 approximately, right? So this is supported currently in our system, right? Beyond this, like if you're working with 15 qubits, so it's beyond the capacity currently, right? With fault tolerant application. So we need to wait a bit for large scale applications of QFT, such as in the source factoring algorithm or even the quantum phase estimation. This is a very good question. What is the difference between running on simulator and running on platform? Good question. So if you are running on the simulator, simulator means what? Simulator means a classical computer plus a trained software. A trained software to run your quantum algorithms, right? Like for example, the QFT. Now it does not have, it is not real. First of all, this is not real quantum computer, not real quantum computer, does not have actual noise behavior, right? Also, it has maximum limit up to HPC capacity. So currently, the HPC capacity is, say, high performance supercomputer has capacity of 2 power 18, right? Exaflop, also known as exaflop capacity, which you convert to up to 60 qubit, roughly 60 qubits. Now, if you are running on the hardware are fast. Hardware, they have a noise behavior. You can see how hardware noise is impacting your algorithm. It can go beyond 100 qubit currently, 100 qubits. So you can map large applications. These are real, not mimicking anything. They are real machines, and it is only required when you, so simulator is good for learning, because you are not paying anything. You are just using your same computer or things, just a software. Good for learning, education, and some basic experimentation. Okay. Now, if your experiment size is large experiment, what do I mean by large experiment? Suppose you're working on, say, 1,000 cross 1,000 MIMO channel, wireless communication. You are understanding the structure of protein. Suppose you are working with machine learning problems, healthcare, for example, For example, the medical images, right? MRI images, CT images, X-ray images. For example, you are trying to understand how the quantum algorithm can help to classify, to identify certain information, etc. on these kind of problems. Then your simulator might not be a good tool. Simulator is not the best option. It's not the best tool. Hope it clears, right? So 60, even 60 qubit may not, because everybody does not have the HPC, right? HPC means the very big supercomputers, right? So even, for example, I'm giving you an example. This is not the true figure, but example. If you have a laptop, if I have a laptop with 64 GB RAM, in fact, okay, I can run up to 20 qubits. So this is a rough figure, okay, like that. Because every a big IIT can have one HPC, right? So one HPC has that capacity, but HPC normally most of us don't have the access to HPC. So in our normal laptop, actually 10 to 12 qubit is for normal laptop. For example, say up to say 16 GB RAM. This is some rough figure based on my experience. I'm telling, there is no math behind this. Okay, fine. Okay, now I'm just giving a 5 minutes break, and we'll come back with the theory portion again, the HHL algorithm, and I'll explain the mathematical details of quantum phase estimation algorithm, the phase trick, and some other important steps how we design algorithm. Okay, so please take a break of 5 minutes. We'll come back at 4:10. Okay, so shall I start maybe? Am I audible and the screen is visible? Can someone confirm, please?
Yes,
Um,
sir.
okay,
Audible.
somebody is requesting for 2 minutes. Okay, no problem. Thank you. Okay, so let's start. So, many problems in science and engineering has their natural representation in form of the linear system, right? So, and we know we are learning these equations from our childhood, right? Let me take the pen. So Ax equals to B equation, right? And we know that this X is a matrix, this A is a matrix, and X is a vector, and B is some another vector, right? Observation vector. So typically, X can be your input to a system A, uh, and you get B, right? This can be your framework. So, and it is common in many places, other econometrics, in normal day-to-day life, your machine learning problem everywhere. This is very common, right? And how we solve it. Now the question, natural question is, can a quantum computing solution solve this problem faster or give certain advantage if we solve this kind of problems, right? And because this problem is very frequent. So our objective is to estimate these X from this equation, right? So if A is a square matrix where A inverse exists, then this is a very easy problem. This is doable, right? And uh, subject to there exists some A inverse with a good condition number. Condition number of A should be quite high, good, right? And further, certain more conditions on this A. But in general, if we don't get the solution of A inverse, right, and there are other type of things. Okay, so let me take some more slides here um, to discuss this problem bit, and then I'll come to the quantum solution. Why this problem is so important. So this Ax equals to B. Suppose A is your M cross N matrix, right? And your X is suppose N cross 1, and B is your say M cross 1. So this is the scenario, right? This is a typical scenario where A is a rectangular matrix, right? So then we typically we cannot do inverse directly. So this cannot be done, right? So this does not exist, right? We cannot do these things. So what we typically do, we do this pseudo inversions, right? Pseudo inversion. And we design a solution like this kind, A transpose A, whole inverse, A transpose B. where this inversion is now done on A transpose A, because A transpose A is a matrix B, where A is now n cross M. This is M cross N, so it is N cross N matrix, right? Now it becomes a square matrix. But still there is question on the stability of the solution. Stability of the solution. Because the condition number of B, etc. Right? But at least you have a solution. And this is known as the least square solution. Right? And people have seen various matrix factorization techniques. I discussed this kind of techniques in QT-03, matrix factorization, that this A can be decomposed into Q and R, where Q is an orthogonal matrix, R is a upper triangular matrix, right? Further, you can decompose A to U sigma V star. So this is known as the singular value decomposition, right? Where U is an unitary matrix and sigma is a diagonal matrix and V star is another unitary matrix, right? And for the matrices where A transpose A equals to A transpose, we have a better decomposition of A, that A can be decomposed as U lambda U star, which is known as the eigenvalue decomposition, right? And then people also derive this X hat computation. So where if you put instead of this A transpose A, you can put all this U lambda U star values there, right? And you can find that this is proportional to f of lambda inverse, okay? F of lambda inverse. So I should put this inside inverse part. So there is a theory called the Cayley-Hamiltonian theory. This theorem says if I can decompose a matrix A to its eigenvalues, right? So if I can decompose A into the eigenvalue decomposition form, like Ax equals to lambda x, or where x are the eigenvectors, lambda is the eigenvalue, or you can write A equals to u lambda u star, then function of A is the function of lambda, or function of this diagonal matrix lambda with the eigenvalues, storing the eigenvalues. Okay. So that means doing the inversion of a matrix is directly proportional to lambda inverse, right? So there is an algorithm called the APSCHE algorithm. Now our equation is this way, right? I have x, I have A, I have P, where B equals to AX, right? So first is that, can I convert this x to ktex? Question number one. This is called a quantum encoding technique. So there is a detailed math why we can do and why we can't do, right? So where this is possible, where this is not possible. So in the beginning, I shared the original research paper of HHL as well as two Qiski tutorial link, right, to understand how the code can be implemented. Although the code implementation is done for smaller system, because these algorithms are the fault tolerant algorithms. Okay. Now A matrix is some matrix, right? And yesterday I told that it has to be a unitary matrix to solve anything or to simulate this thing. So I have to convert this A to U, right? Because then only I can generate reversible logic using this unitary matrix. But the condition is U star U equals to identity matrix, right? And U can be decomposed into the certain coefficient type Pauli words. A are certain coefficients, and this pi can be your Clifford gates or non-Clifford gates, Clifford and non-Clifford gates, right? So I'm not going detailed of this. The mechanism, may I know where we can find these research papers and codes, sir? I beginning the class, please scroll up the chat box. Okay, I am just, if I am allowed to copy paste, I can do it again. Let me share it again. Copy the link. Just to wait, I'm just pasting it again. Please save this link, okay? I'm just sharing once again all these 3 links. Please save these 3 links. There are very good tutorial on this thing because explaining a entire research paper in 1 hour is impossible for me or for anyone, in fact. But I am trying to explain the philosophy behind this algorithm, how it works with our classical understanding of linear algebra. Okay. So one story is that I can encode x to get x. I have to convert a to u, right? And then I need to design a solution, of course, because I need to estimate this one because this is unknown, right? I have to do this. This is unknown. First, I have to, a is known to me. This, in this equation, ax plus ax equals to b. This is known, this is known, this is unknown. In general case, right? We have to estimate this in linear system solving. In engineering, the reverse thing can happen. Suppose sometimes we know our input and output, we understand, we try to understand the system itself, characteristics of the system, right? Then A is unknown there, right? Sometimes we know the input, we know the system, but we don't know what will be the outcome, right? So that then B is unknown. So this can happen. The equation can come in very different nature, differently, but in general, for now, I have to estimate this X, right? So what is given? B is given, A is given. So of course, B should have to convert to some quantum state KB, right? Some encoding I have to do. And this encoding has not to be done because this is the ultimate answer you are expecting. But you have to convert this and this. Now the protocol that A to U is done is called the Hamiltonian simulation protocol. Hamiltonian simulation protocol. Hamiltonian simulation protocol, which convert a Hermitian matrix or a symmetric matrix A to U. And you can ask if it is not a symmetric matrix. In this paper, it is shown that you can design a matrix B such that this 0, A star 0 is another Hermitian matrix. And then you can design the algorithm on B. This was just an augmentation method applied here. How to convert any matrix to a Hermitian matrix, right? So this is a protocol A to U we have to do, B to get B we have to do, right? And then we have to find a solution. Now, today I'll show an algorithm called quantum phase estimation algorithm. Okay, and the objective of this algorithm is that given an eigenstate psi and an operator u, right? You can represent this as e to the power I theta of psi, right? Given a psi and an operator, you can estimate its eigenvalue of that particular operator, right? And that particular eigenvalue, because it's a unitary matrix, they have the eigenvalues lambda k. You can write it as e to the power I theta k because they all have modulus equals to 1, right? And they have different phases. Okay. So instead of estimating the lambda eigenvalue, you can directly estimate the theta. You are done. That's why it is called phase estimation algorithm, quantum phase estimation algorithm, right? And that is one of the vital step both in source factoring algorithm as well as in the HHL algorithm or the Harrow-Hassidim-Lloyd algorithm. That's why this subroutine is very, very critical. Okay. So that's why the eigenvalue of a unitary matrix always lie in the unit circle. So you can see the phases are different, but their amplitude are all are equal. These are the eigenvector of a unitary matrix. Okay. So what are the protocol in this algorithm? Just quickly let us, I'll share the PPT, don't worry. You don't need to take notes of the HHL algorithm. I'm just explaining how it is done and why it is done. And then you can read the research paper. It's a bit difficult research paper, I would say, for the beginners. But don't worry, because there are lots of protocol involved in this solution. And still people are working on this algorithm. It was, this paper came in 2009. 2009 this paper came, and this was the original article. And still people are working on it for real-time app implementation, right? So implementation is very challenging for this algorithm. So there is a 2x2 implementation I have shown you in the Kiski tutorial, but the steps are not that easy. I mean, for each and every step, the encoding part is easy, but there are other vital steps. So in general, when we solve this HHL algorithm on a classical machine, what is the complexity? So you are doing a matrix inversions, right? So normally it is order of n to the power 3 or more, right? And with certain sparsity condition, that if the matrix A is sparse with the sparsity S, and condition number of that matrix is K, right? Then the best classical algorithm, that is the conjugate gradient method, right? So that is basically some order of nk, something like that, right? And if you are using the HHL algorithm to find some function of the input, some subset of the equations you want to solve, and the equation has enough sparsity, then you can reach up to order of log n s square k square by epsilon. So there is a reduction of n to log n is possible, subject to that matrix is sparse enough, has a good condition number, and this epsilon is basically when you are converting a to u. So how much error, because u is e to the power minus iat, right? So actually u to u tilde, how much error you generate. So that also impact the solution. So it's a function of 1 by epsilon, right? So ultimately it's a logarithmic like the n to log n exponential reduction in the complexity, subject to it's a highly sparse system, and you are only looking at some subset of the solution, right? So of course, our final solution will be coming as a inverse b ket, which is basically ket x, because this is equivalent to x equals to b, right? So this is the form of the thing we are expecting, but we are looking at some expectation value given to certain measurement operator m, right? So in simpler terms, what are the things we have to do? Okay. Okay. There is, I don't know how to speak in the simpler terms, but I'm trying. Okay. Because this algorithm has a lots of embedded steps. Okay. So of course, the actual solution that I was discussing, like what are the component of a linear equation x equals to b? So b part, you should have an encoding to ket b. A cannot be directly done on quantum. You need to encode an u corresponding to A, right? And then if you identify the eigenvalues of this lambda, right, you also understand the eigenvalue of a, because this u equals to e to the power minus iat, right? And if you are getting, because the lambda of u, right, and I told the Cayley-Hamilton theorem that if you know the lambda, so you know the certain properties of the matrix for sure, right? So this is the characteristics equations you can always express for the matrix to with its eigenvalue, right? So hence inverting a matrix is related to inverting its just a eigenvalue 1 by lambda, right? So is there a quantum protocol which can calculate this one, right? That is the objective of HHL algorithm, right? In simple words. Now, how to do this part? So there is a diagram. So first because you have the state B, right? Kate B that you need to encode here. So there are three types of qubits basically. One is called the controlled qubit. So let me give the name. So the names are input registers, clock registers, and ancillary registers. Three types of qubits you need to use. So in the first set of qubits, so you load this particular thing, and another set of auxiliary qubits are required for the algorithmic propagations. So first we do the quantum phase estimation algorithm to find out the eigenvalues of the system, right? Matrix. And once we get the eigenvalue of the matrix, we invert the matrix. We get the lambda hat from quantum phase estimation, but we have to convert one by lambda. We have to prepare, right? And this main contribution of HHL algorithm is directly converting from a matrix A to U to 1 by lambda. This is the one of the main contribution. Okay. Now, once you do these conversions, then you have to do certain post-processing part. So you have to uncompute certain things, right? Because any estimations you want to do, you have to do this part, right? So for example, x part is your expectation value, right? So, and this post-processing, if you do, then only you can uncompute and get the post-process value in terms of this get x that is proportional to A inverse B. So I sincerely request everyone to, so there are the detailed part is there, like how to do that. So basically any matrix you can do eigen decomposition this way. So all these steps, basic steps I already told. And there is a good answer basically, I should say, or good educated gaze of the state B, that was our observation vector, that any quantum state, right, if it is a quantum state, right, you can always represent in the computational basis, for example, Ci Kt, right, over I. So it can be, say, C0 Ket0 plus C1 Ket1. You can also this in the eigenbasis of the actual matrix. Say Di and Ei, where Ei, this is because of the superposition principle, superposition theorem. So basically, you can represent a quantum state either in computational basis or in eigenbasis, right? So that's what this particular protocol used here, that representing the state vector in the eigenbasis of the original matrix, right? And then basically they are trying to compute the ktex, right? So there are individual steps. This is the ultimate objective, okay? So the underlying steps are quite broad. Most of them are the QPE, quantum phase estimation, that I'll discuss today. So I have roughly 20-25 minutes. So let's discuss how this QPE works. If you understand how to compute lambda, then you know how to do 1 by lambda, right? So there are some more steps. So one of the fundamental step of HHL is the QPE algorithm, and let us do that one. Okay. So I'll share the notes. Don't worry. So and by doing this algorithm, you basically boils down the complexity to uh, log n s square k square. Okay. So that means you can make faster computation for solving linear system of equation. So let's go back and again, yeah, likewise, yesterday we'll go ahead with this QP or quantum phase estimation. Actually, for individual, um, can you compare the same with classical? I started with the classical thing, right? Beginning, I told everything like QRD composition, all those things. So individually, if I if I uh, if I could take the QP and HHL algorithm as two class, that could be better. But as I don't have time due to some of the official work, so I'm merging these two classes. So I'm sorry for that. But still trying to at least give the fundamentals quite clear, because anyway, I believe there will be quantum algorithm course, and if I am there, so I'll go much detailed of each and every individual equations and their explanation. So HHL again will come back to us. Okay, but this QP and QFT are fundamental. You have to understand this. Okay. Acha, so I'm not doing the recap part because it will again take a lot of time. So let us directly. So this is important, just that we say it. U of quantum state psi equals to e to the power I phi or theta, whatever you say, right? So this is just like x equals to lambda x equations, right? Eigen equation. Yes, yes. So I shared these tutorials. Exactly this kind of problem was solved in the tutorial. Please look at the tutorial. So these are explained very well in the tutorial. So the link I provided. Okay. So the question is, um, unitary matrix has eigenvalues of the form unitary matrices like U, okay, um, have eigenvalues of the form e to the power I theta, right? And it has eigenvectors that form an orthonormal basis, right? It has eigenvectors. All the eigenvectors of a unitary matrix, they form an orthonormal basis set, right? So, and it has, or they have, I should say, they have eigenvectors that form an orthonormal basis set. Examples, there are pretty lots of examples there in the links I provided. Why I am taking the QPU part? Because nobody will explain this most important fundamental routine of HHL. Okay. That's why I thought to give this much detail on the fundamental, because bigger algorithm anyway will come back again in other courses anytime. But this fundamental step, how the QP work, is the most important fundamental for HHL or any major algorithms like source and all. So this is important. So the question is, so what did I say in this sentence? Because we normally break a matrix or basically decompose a matrix into, say, u lambda u star, right? Similarly, so this u is some unitary matrix, right? Suppose, okay, so let for clarity, a equals to, suppose, e lambda e star, right? Where e is some unitary, right? Now this a can be converted into u using the Hamiltonian simulation protocol, where u equals to e to the power iat minus iat, right? By Planck constant h bar, but you can take it as 1, for example. So this u, if you do mathematical decomposition instead of a, right? And suppose you get uh, this u has a decomposition of, say, f lambda tilde f star. Now this f matrices, they have suppose f1, f2, these are the column vectors, right? So they are all orthonormal, orthogonal to each other with their norm equals to 1. Tutorial link I just provided, right? Somebody asked, and 3 links I just provided. Please look at the message. 3-4 times I requested to download or keep the link. At 4:23 p.m. I just shared the 3 links. Please, everyone, again I am requesting to please copy this link. Again, I am just putting in the chat box for the tutorial link. Please copy and paste these links, right? So this orthonorm, the columns of this matrix F are the orthonormal vectors, as well as this matrix lambda tilde, all the eigenvectors e to the power I theta 1, e to the power I theta 2, and so on, e to the power I theta n. So they are the unit vector, I mean the amplitude 1 with the complex coefficients with phase theta 1, theta 2, theta 3, and theta n, right? This way. And our objective is to estimate this theta I, right? Suppose given this u of psi I, suppose psi I or fi is your psi I here, right? F1 is psi 1, psi 2, and so on. And our equation is e to the power phi I, or phi I and psi I. So this is my eigenvector, this part, and this is my eigenvalue with phase theta phi I or theta I, whatever it is. Okay. And I need to estimate this phi I or theta I, whatever it is. So if I can estimate this, I have estimated lambda I have done for u, I have done for, so these are, I have done for u, I have done for a, and that means I have done for a inverse also. So these are related this way. Okay. So how to do these post-processing things in the paper, these are very much detailed. But this estimating this phi I is the critical step. Okay. So let's do the algorithm that it is done is called the quantum phase estimation algorithm. And the first step to do this is called something known as QPE trick. Okay. So let's draw a circuit with me. This is a controlled U operator, okay? CU operator, controlled unitary operator. This is a Hadamard gate. Hadamard gate. We started with two sets of quantum resistor. One started with the state 0, another we started with the state psi, and we'll see what happens at the output, right? This particular circuit. And suppose this is our step 0, step 1, step 2, step 3. I hope everybody has drawn this picture. Now we'll do the mathematics, okay? Step 0. So step 0 में क्या है? What is the thing in step 0? So it is nothing like 0 and psi. So it's 0 tensor product with psi. This is my state here in this particular point, right? Now I have to look in this particular point. What is my composite state? So step 1. Step 1, I have done the Hadamard gate in the first qubit, right? So my state here is plus state. And my state here, it is again 0 psi state because I have done nothing, right? So I can write this first step as 1 upon square root 2, 0 plus 1, that is my plus state together, right? And psi. Or this can be written as 1 by square root 2, 0 psi plus 1 psi, right? Now there is step 2. So that is, we are applying the controlled unitary gate across the two qubits. I mean, applying the U gate in second register and controlled from the first register, right? So if we do that, what will happen? So 1 by square root 2. First qubit is 0 means it will do nothing to the second qubit. So 0 psi will be intact plus first qubit is 1. So it will add, it will basically change the phase of the second qubit. So that means 1 and basically r theta, say some particular phase, that phase of the u theta gate will be multiplied here and the state psi like this, right? So this r theta is basically rotation gate with angle theta, right? Now step 3, again you are applying the Hadamard, right? Hadamard here, right? So then if the state is 0, it will be plus. If the state is 1, it will be minus, right? Plus means 0 plus 1. This will mean 0 minus 1, right? So if this is the case, then third step will be 1 by square root 2. This 0 will be 0 plus 1 upon square root 2 psi plus r theta, right? So, okay. So I can write as 0 minus 1 by square root 2 r theta or r phi to get psi, right? Now it will do all the changes, right? Suppose I'm just writing r theta as e to the power I theta because Anyway, this is equals to your 1, 0, 0 e to the power I theta, right? This is the gate. Just I'm replacing this matrix with this scalar quantity just for easier calculations, right? So then this equations, if I put all 0 one side and all one other side, then what I have is this square root will come outside, then square root 2 times the square root 2 will become half, right? And I'll have an equation like this: 0 and 1 plus e to the power I theta. Just I placed r phi as e to the power I theta here, right? Plus 1 into 1 minus e to the power I theta or I phi, right? Else you can write in the matrix form. So the matrix form, if you write, so this I you can write as identity matrix. 1 will be your identity matrix, and e to the power I phi you can write it as r theta. That form also is fine. So this looks good because why this looks good? Because when you do measurement, so then this thing will become the probability of getting the 0, right? Probability of getting the 0 will be equals to 1 half of this 1 plus e to the power I phi square, and probability of getting qubit 1 will become half of 1 minus e to the power I phi square, right? And it is not equals to probability not equals to half of individual qubit, right? So this is called the quantum phase trick, and by this I can potentially manipulate the probability where I can start with basically I can start with something like this. Suppose this is my superposition state initially, but I can create a superposition such that I can manipulate this probability. I can maximize this, I can minimize this, or whatever I want to do, I can do using this theta by controlling with the theta. If you take theta equals to 1 degree, you can make this value to 0.9999, and this can become 10 to the power minus 5, roughly, approximately. Okay. So no, this is the psi state, right? So when you do measurement, so after measurement, your state is 0 times psi and 1 times psi. So your quantum state collapsed. So you're getting the probability amplitudes. Right? So up to this, you have the psi state. After this, you have the state either 0 psi or 1 psi. It after the measurement. So this is the phase trick part. How by just controlling the phase of a unitary matrix taken as a control unitary way in a controlled fashion, and I can change the theta of that matrix by certain policy, right? Such that I can manipulate the probability. I can do interference a lot, right? Superposition. I created the superposition with Hadamard, and now I create the interference, controlled interference, right? Or sometimes when you break this big CU gate, you will see some of the part of the interference are done by entanglement, some of the part are done using certain simple rotation gates, right? Physicists may disagree, okay, but computationally, that's what we do, okay. Okay, so let's do it for n qubit system. How much time remaining? 4 minutes. Okay. Not to worry. I'll just quickly draw the circuit, and then basically I'll share the notes. Maybe that might be a better thing. N qubit, for that you need many such zeros, and you need to encode many such superpositions to get n, right? So you have all such circuit component. You have an encoded state psi here. So here in this particular case, you have to do u to the power 2 to the power n minus 1 to create various phase factor. Then u2 to the power 2 to the power n minus 2 dot 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 up to u2 to the power 0. This is how we do. Right, and this is done like this: first qubit to first register, second qubit to second register, last qubit to last register, in this way, right? So once you do this way, if you design the circuit in this way, okay, so then your final state will be, I'm just writing the final state equation, right? That will be 1 by 2 to the power n. Just if you compare with this particular equation, so this is how many qubits we have used? 2 qubits, right? So that's why 1 by 2 to the power 1 by square root 2 square, and that becomes half in the equation here, right? So similarly, it is 1 by square root n to the power n, and so you can do it by hand also. I'm not because of the time is limited, I'm just writing the final expression. You can write in the step 1, step 2, step 3, step so on, and you'll get the final expression as 0 plus e to the power phi I 2 to the power n minus 1 get 1 tensor product. Just yesterday, like we derived for QFT, similar kind of derivation we have to do. Get 0 plus e to the power I phi. Psi is not required, might not be, because I've been put earlier. To the power I phi 2 to the power n minus 2, 2 to the power n minus 2, get 1 tensor product, so on. Last term will be get 0 plus e to the power I phi 2 to the power 0, get 1. So please allow me 2-3 minutes more. Just I want to complete this part, because otherwise it may not be possible to do things. So if you look at this particular equation and compare with the QFT, okay, quantum Fourier transform, this x tilde in quantum Fourier transform was 1 by square root n 0 plus e to the power 2 pi I x by 2 1 2 to the power 1 get 1 dot dot dot. Last was, sorry, it just got called, and that's the problem. And the last was 0 plus e to the power 2 pi I x by 2 to the power n 1. So if you look at between these two equations, like QP equation, quantum phase estimation equation, and quantum Fourier transform equations, they are almost same thing. But here I can see the power of 2 in the fraction in the denominator, and it is in the numerator. So as if the QP is similar to QFT, quantum Fourier transform, except the condition that this theta or phi in the QP is actually phi in Fourier transform as pi by 2 to the power n into 2 pi. So there is two terms. One is the 2 pi term, another is the 2 to the power n term, right? So I have to uncompute this part, right, in order to estimate this theta component, phi component. So that's why in the circuit we'll see first quantum phase estimation circuit, then there is a inverse quantum Fourier transform, IQFT circuit. IQFT circuit to uncompute the other part, and what you will left with is 2 to the power n 5 as a quantum state, right? So in the HHL algorithm, we'll see that in the construction of the whole QP circuit, first part of the circuit will give you this quantum state, and if you multiply with inverse quantum Fourier transform, just as you design the QFT circuit, if you design the IQFT circuit, inverse quantum Fourier transform, the reverse one, right? So if you multiply these two block each other, what you will left out with this 2 to the power n times this 5 part, right? So this is your first, this particular part. So that means you from here, whatever result you get, if you divide with 2 to the power n, so you will by result divided by 2 to the power n number of points, you'll be getting the phi as your estimate in the beginning. In the Fourier transform, we are looking at that particular thing. And once you get theta thing, then you can know e to the power I theta hat. So that is your lambda, right? Once you get the lambda, you know the 1 by lambda. That means you can calculate the A inverse, right? So this is the way that HHL work. But of course, this is not that simple. There are the state conversions are like obeying certain important equations. So we have to appreciate the assumptions and underlying principles. But eventually, this is the simplistic versions we can consider for now. So with this, I conclude my session here. And if you have any questions, feel free to ask me. And I'll be sharing the notes. No need to worry.
Thank you very much, sir, Dr. Mustafizur Rahman. Yeah, participants, if you have any questions, we have another 1 or 2 minutes you can take. Otherwise, we will conclude today's lecture and then we'll again meet on Monday. Importance of last algorithm is what he's asking.
Okay, importance of the last algorithm. What is the last algorithm? Is the HHL one. HHL is the linear system solver algorithm. So if you have any linear equations, right? So it is very common in most of our communication engineering systems, signal processing, image processing, everywhere. Linear system is very common equations, right? So can you use quantum computer to solve linear system of equations? So HHL is the algorithm to help you to solve the linear sets of equations, right? So for those kind of problems, so this is an important tool, quantum computing tool. Yeah.
Lakshmi Narasimha, sir, are you saying that it is no, or can you name the algorithm that you are
HHL you are saying, or which one? QP, quantum phase estimation?
QPE.
Yeah, quantum phase estimation is the basic fundamental subroutine of many algorithms, right? So this is like a building block. Okay, building block for like source algorithm, HHL algorithm, Grover's algorithm. Many algorithm has this fundamental routine. So in the very basic block, we have seen how controlled unitary gate, in addition to two superpositions and a controlled unitary gate, that is called the phase trick circuit. You can think as a smaller version of the QP circuit that helps us to basically manipulate the probabilities, right? And create certain interference pattern. I am telling in the physics way, interference pattern such that I can maximize the probability of certain computational basis and minimize the other basis. So that is one of the very important subroutine in computer science. We say subroutine, right? That is the building blocks of an algorithm. So quantum phase estimation is so very important subroutine for many quantum algorithms. Grover's algorithm, source, HHL algorithm. So this is also a fault tolerant algorithm. So you can run the full version of this algorithm in the upcoming logical qubits, like error corrected qubits, or the more number of qubits is required to implement this kind of algorithm in full scale.
Yeah, thank you so much, sir, for your valuable time. I think 4 full hours you have engaged, and then, yeah, thank you so much. Once again, participants, some of you were asking, the book is called QT-0 and QT-1 by Dr. Mustafizur Rahman and his colleague, Dr. Richa Goel. Both of them were teachers in our courses. So please buy the book. Don't ask for soft copy. That is kind of plagiarism. So please try to take it. It's not very costly. That's why I said 450 rupees. So please try to take it. And the details are posted already in the group. You can follow it.
Thank you.
So Mustafizur sir was there for us. So this will be his last class. So thank you so much, sir, for being with us, and we will meet again in QT-06. So
Thank
till
you
that
so
time,
much. Sure.
take a break. Thank you. Thank you all participants. And I think we will ask him to join us for the valedictory session. At that time, we will have some special remarks from him, right?
Sure.
Thank you. Thank you so much, sir.
Thank you. Thank you, everyone.
Participants, the announcement is regarding quiz 2, which will start in about 1 hour from now. At 6 o'clock, we'll start the quiz 2. So, quiz 1, if you look at it, quiz 2, you have, uh, uh, we are giving time till Tuesday, right? So, please don't worry because today some lecture was covered.